This meeting is being recorded.
That's all clear for everyone. Okay. Want to maybe slowly start getting into it then, you think, guys? Or
yeah, let's go ahead and start.
Yeah. Okay. So hello, good morning, good evening, good afternoon, and welcome back. Today's talk is from Christian Drago from the University of Toronto on aspects of two-photon absorption of squeeze light and the CW limit. So without any ado, I shall hand it over to you, Christian. And if you have any questions, people, just put them in the comments and we can interrupt if it's urgent. Otherwise, we can come back to that at the end. Okay, take it away, Christian. Thanks.
Perfect. Thank you for that introduction. So hi, everyone. My name is Christian Drago, and I'm a PhD student at the University of Toronto. And this work was done in collaboration with John Sipe. So before I begin, I'd just like to thank the organizers for setting up this seminar series and also, allowing me to present. I'd also like to apologize in advance because this will be a theory talk, and I understand there's a lot of experimentalists in the crowd. And as with most theorists giving talks, I tend to overdo the equations. So, since we're all familiar with the motivation, I'll begin by mentioning that there's been a large amount of theoretical work in the far-detuned low-flux regime. More recently, however, a new theoretical initiative has been led by Michael Raymer's group, who just a few weeks ago extended their results and considered the far-detuned high-flux limit. So with this work here, we hope to extend past treatments and consider both the near resonance limit and high-intensity regime of two-photon absorption. So to do that, our goal is to develop a model of two-photon absorption, which we can use to explore a wide parameter space. We're going to consider incident states of light, where we're going to neglect focusing effects as well as dispersion, and consider the response of a single atom or molecule. Within our model, we want to be able to consider both pulsed or CW sources, consider the case where an intermediate state within a two-photon transition can be near a one-photon resonance, as well as consider both the low and high intensity limits. However, today we're just going to specialize to CW coherent light and squeezed light pumped by a CW source, which I'll often refer to as CW squeezed light. So here's an overview of this talk, and I'll begin by describing the model itself, which is shown by this level diagram. We have a ground state G, an intermediate state E, and a final two-photon excited state F. We work in the limit where the incident field is always resonant with the two-photon transition. And we will explore the resonant behavior of the intermediate state by considering different energy levels of the state E. And finally, within our model, we also want to include two sources of broadening, the non-radiative decay of excited states as well as dephasing. And both of these effects will be contained in these broadening parameters, gamma E, G, and so on. So the Hamiltonian for our system is partitioned in the usual way, where H0 is the free Hamiltonian, given as a sum of the molecular contribution, the radiation field. And then we include a quantum reservoir, which we use to model the non-radiative decay of excited states. The interaction is given between the molecule and the field in the rotating wave approximation. We include the molecule in the reservoir, and we include this time-dependent stochastic fluctuation so that at the end of the calculation, when we take the classical expectation value, we reproduce the effects of dephasing in the appropriate limits. So we're going to set the dipole moment connecting state F to state G to 0. And in doing so, we're neglecting all one-photon transitions from G to F, as well as any radiative decay from F back down to G in the form of fluorescence. But we'll take it one step further and completely neglect radiation reaction. And in doing so, we'll expand the use of the quantum reservoir to, at least in this case, phenomenologically model fluorescence. So now I'll begin the discussion of what we calculate, which is the absorption. So in past treatments, the probability of the molecule being promoted to an excited state is calculated, and this is referred to as the absorption. But here, we find it useful to just directly calculate the energy removed from the incident field, and we find this to be true, especially in the CW limit. So let me remind you of the classical picture. where we have an incident electric field interacting with a charge, and one can calculate the total work done on the charge, or the absorption, as the time integral of the electric field dotted with the time derivative of the classical dipole moment. Now, moving to the quantum case, within our assumptions, we can begin with the Hamiltonian and directly calculate a quantum version of the absorption. And we find it's given by this form here, and we can compare it's similar to the classical result. And we make the approximation of neglecting radiation reaction in two places. The first place is where in the classical case, we would have the full electric field. In the quantum case, we replace the time evolution by the h0 time evolution. And the dipole moment of the molecule, the time evolution of it, is given by the full Heisenberg equations of motion, again with the replacement of each field operator by its h0 time evolution. So here is an expression for the energy absorbed from the incident state of light. So working with this equation, we can solve it perturbatively up to fourth order, and we find that it's a sum of 5 contributions. The first contribution, which is the lowest order contribution, is given by this form here, where it's a product of 2 functions. This left one is going to be a broadening function, which is going to contain line widths like gamma EG, and it's multiplied by this energy density per unit area, and depends on this 1 photon correlation function, which is going to contain the 1 photon statistics. Each higher order contribution, A2 to A5, can be written in a similar way, where now we have these higher order broadening functions, which can contain various combinations of the gammas, and this energy density squared per unit area squared, which depends on this 4-point correlation function and contains all the 2 photon statistics. So the way each of these terms contribute to the total absorption is as follows. A1, which is the lowest order term, depends on the perturbative expansion of this double-sided Feynman diagram. And specifically, it's the population in the ground state at 0th order and the absorption of a photon. So A1 is the usual 1 photon, lowest order contribution that I think most people are familiar with. The next term, A2, is generated from the higher order correction of the population in the ground state, as well as the lowest order non-zero contribution to the population in the intermediate state and the emission of a photon. So because this depends on the second order correction as well as the emission, A2 will directly correspond to the saturation of the total 1 photon absorption. Next is A3, which is generated from coherence between the ground and final state and the emission of a photon, and will involve a virtual 2-photon transition from G to F. In general, A3 will have a strong dependence on the detuning from resonance, but in the far detuned high intensity regime, we find that A3 will contribute to the total 2-photon absorption. A4 depends on the population at second order and the emission of the absorption of a photon. It will contribute to 2-photon absorption and is more often referred to as the sum of the rephasing and non-rephasing pathways. And finally, A5, which again depends on coherence between G and F, and now the absorption of the photon on the left. As well, we'll find this term can have a sensitive dependence on detuning, but it will contribute to 2-photon absorption and is more often referred to as the direct quantum pathway. So with this understanding of each term, we define the total 1-photon absorption to be the lowest order contribution plus its saturation, and the total 2-photon absorption to be the sum of A3, A4, and A5. So with the model and absorption discussed, I'll now begin talking about incident states of light and starting with CW coherent light, where a coherent state is given by the displacement operator acting on the vacuum. And we're interested in the CW limit, where states of light are given by this form here, where the field is oscillating at some frequency for a length of time. And in the CW limit, we take that time to infinity. So we model this by the spectrum given by a sinc function and identify the bandwidth to be omega p. In the CW limit, we take this bandwidth to 0, and then this spectrum is going to be strongly peaked at the center frequency, omega bar. Moving to our model of CW squeezed light, we start with a squeeze state, squeezing operator acting on the vacuum, and this is the form of the squeezing operator. We work in the degenerate limit, in which the photons that are generated are each centered at the same center frequency, omega bar. Gamma is going to be the joint spectral amplitude and is a product of the pump function and the phase matching function. So we're interested in the CW limit, where the joint spectral amplitude is going to be given by this form, where it's strongly correlated in the anti-diagonal direction with a width given by omega E, and we identify this to be the bandwidth of squeezed light. And in the diagonal direction, it has a width given by omega P, which corresponds to the bandwidth of the pump, which in the CW limit is going to be going to 0. So within this model, we neglect dispersion or assume that it's been compensated for. And as a simple model to make calculations, we take the phase matching function to be constant for frequencies within the bandwidth and 0 otherwise, so just a sharp cutoff. And then we identify the entanglement time to be 2 pi over that bandwidth, the time scale in which photon pairs are correlated. So within this model, we can directly work out a squeezing operator transform, which allows us to calculate the correlation functions. And as a check, we'll just calculate the G2 correlation function in frequency. So it's shown here as a sum of 3 contributions, where the first contribution is previously labeled as a cross correlation or coherent contribution by Diane, in which the photons that participate are anti-correlated to always sum to the pump. And then we see 2 other contributions, which are labeled the autocorrelation or incoherent contributions, in which we see a fixed background plus a correlation along the diagonal. So as mentioned, some of this nomenclature was mentioned by Diane in 2007. And for a more recent experimental paper where one can see these 3 contributions, at least when dispersion was included, one can check out Maria Chakova's paper here. We can also calculate the correlation function in time. And when we evaluate it at equal times, we see it's the usual 3 plus 1 over sin squared of beta naught being the gain parameter, which is the usual result that one finds. So with the model discussed and our incident states of light, we begin this discussion of each absorption term with those states of light, starting with the 1 photon absorption, where for coherent light, it's given by this form here. It scales linearly with intensity, which is not surprising, and depends on this sigma 1 coherent cross-section, which I'll show later on. The 1 photon absorption for squeezed light, again, scales linearly with intensity. But I want to point out that these cross-sections will be in general different because for squeezed light, we have the potential for a large bandwidth, which may overlap with resonant intermediate states, changing the value of this cross-section compared to the coherent light result. Moving to each higher order absorption term, we start with the coherent light result, which scales quadratically with intensity, which is again to be expected for a classical source. And this higher order cross-section I'll show later on. And we compare that to the higher order result for squeezed light in the CW limit. And we see there's 3 contributions or 3 scalings with intensities and 2 unique cross-sections, where this first cross-section is labeled sigma squeezed Roman numeral 1 and sigma squeezed Roman numeral 2, again, which I'll show later on. So to begin, we see that this first contribution has a linear scaling with incident intensity and is multiplied by this IVAC, which we refer to as the vacuum intensity and is the energy of each photon passing through the beam area within an entanglement time. And we use this notation because a similar quantity was defined by Klitschko in 1982, so we find it useful. So also what is apparent in this first contribution is a quadratic scaling with intensity. So we see both a linear and quadratic scaling, which is multiplied by this cross-section, which as I'll show is going to come from the cross-correlation or coherent contribution. In other words, this contribution is going to involve photons which are anti-correlated and always sum to the pump, and it involves both a linear and quadratic scaling. We also see a second quadratic scaling with intensity, and it's multiplied by the second cross-section, which, as I'll show, is going to come from the autocorrelation contribution of the correlation function. So this equation for the absorption that we've derived, at least within our assumptions, is fairly general in that you can see that it's definitely valid both in the low and high photon flux regime because it has a linear and quadratic scaling. But the cross-sections themselves, as they're defined, are also fairly general because they're valid near resonance and for any broadening parameters. So we can compare this to an earlier result given by Fay, where a probabilistic argument was used to derive that, at least initially, that the rate of 2-photon absorption was given by this form, which I think we're all familiar with. And we can see that we have extra contributions, but later on in this talk, I'll show that at least in the appropriate limits, this equation will reduce down to this earlier result given by Fay. So with the absorption terms discussed, I'll now begin the discussion of each cross-section and actually show you where they come from and how they're defined. Starting with the lowest order contribution for the one photon absorption, considering coherent light, where using usual methods, we can calculate the correlation function, the one photon correlation function. We find it's proportional to the spectrum squared of the coherent light, which in the CW limit is going to be strongly peaked at the center frequency. So in that limit, the one photon absorption cross-section is just the broadening function for that absorption pathway evaluated at the center frequency. So if the broadening function is a Lorentzian, which it turns out to be the case, we just pick out the frequency at omega bar, and then our detuning is just the difference between these two frequencies. And of course, in the way that we've defined this, it has the usual units of area as expected for a cross-section. Moving to the squeezed case for one photon absorption, again, we directly work out the one photon absorption correlation function. We find that it's fixed for frequencies centered at omega bar within the bandwidth. So whereas before we had this picture of a Lorentzian and evaluating it at the CW coherent light frequency, the situation now is we have the potential for a large squeezed light bandwidth, which we need to take into account. So the cross section for squeezed light is essentially going to be the overlap of these two functions. And that's exactly what we find it to be. It's an integral over the broadening function over the bandwidth of squeezed light. Moving to each higher order cross section, we start with the 4-point correlation function for coherent light. Again, it's worked out using usual methods, and we find that it's a product of the 4 spectrum functions. Again, in the CW limit, each of them will be peaked at omega bar, which means that the higher order coherent light cross-section in the CW limit is similar to the lowest order. It's just each frequency evaluated at omega bar. And in the way that we've defined this cross-section, it has units of area per intensity. So moving to the correlation function for squeezed light, we can directly calculate it and find 3 contributions, where as a reminder, alpha is the pump function, which in the CW limit is going to be strongly peaked. So we find that the first contribution is this cross correlation or coherent contribution mentioned by Diane, where the photons that participate are anti-correlated and sum to the pump. And the second 2 are the autocorrelation contribution, in which there's still correlations between photons. That is, omega 1 will be strongly peaked to omega 4, but those correlations are on the bra and ket side of the correlation function. So more recently, Michael Raymer's group calculated a very similar equation in their recent archive paper. So with this equation for the correlation function, we work out the cross section, starting with the sigma squeezed Roman numeral 1 cross section, where we can see that the frequency dependencies of the broadening function are now anti-correlated. So this first cross section is directly going to come from the cross correlation, and we expect this contribution to be dominant for absorption pathways which involve a virtual 2-photon transition, because the frequencies that participate will always be resonant. The second contribution to the cross-section is given as the average of the autocorrelation contributions. And specifically, I just want to point out that this contribution here has a frequency dependence where the second and third frequency are the same. This means that for absorption pathways involving intermediate state populations, like specifically the rephasing and non-rephasing pathway, we can get like a double resonant effect. Essentially, when the first frequency is resonant, the second one will be, when the second frequency is the third one will be. So we expect this term to be dominant for that absorption pathway. Now, with all of our terms shown, we can begin discussing them in various limits, starting with the narrow band limit, where we take the bandwidth of squeezed light to be much less than our broadening parameters. So whereas before we had this situation of integrating over the overlap of these two functions, the line width and the squeezed light spectrum, in the narrow bandwidth limit, we approach a case like this, where the good approximation, this is just again the coherent light result. So we find that the lowest order 1-photon absorption cross section for squeezed light in the narrow bandwidth limit to good approximation is just the coherent light result. And similarly, each higher order squeezed light cross section again approaches the coherent light result. And in this limit, it's very straightforward to compare the 1 and 2 photon absorption because the cross sections are the same. And we find the ratio of 1 photon absorption is exactly equal to 1, I think probably as expected. And the ratio of 2 photon absorption of squeezed to coherent light in this limit is exactly equal to the G2 evaluated at t equals 0, which is in agreement again with Michael Raymer's recent result in the same limit. And in our notation, G2 can be written as 3 plus the ratio of the vacuum to squeezed intensity. So we expect a large enhancement when however, here, because we're in the narrow bandwidth limit, which means the bandwidth is smaller, conversely, the entanglement time is large compared to the decay times of the molecule, we really don't expect a large contribution here. So to good approximation, squeezed to coherent light in this limit is just a factor of 3 given by G2. Next, we consider the broadband limit, where by broadband, we take the bandwidth to be larger than each broadening parameter. And we're going to make some plots. So to do that, we have to set some parameters. And I'll start by setting gamma EG, which we take to be 0.01 terahertz. And this value is motivated by the fact that in the far detuned limit high intensity regime, we want to ensure that 2 photon absorption dominates. We set gamma FE and gamma FG to be 1 terahertz. This is motivated by typical fluorescent dyes and ensures that the classical 2 photon absorption cross section, which we calculate, is on the right order of magnitude. We take the center frequency to be 357 terahertz and the bandwidth to be an order of magnitude larger than the largest broadening parameters. So then our parameters satisfy this inequality. And I'll begin by discussing each term, starting with the lowest order contribution, the 1 photon cross section. So here's the classical or coherent light cross section plotted as a function of detuning on the x-axis and meters squared on the y-axis. We see it's fixed near resonance and then decreases with a 1 over delta squared dependence in this far detuned limit as expected for a 1 photon absorption term. So we now overlay the squeezed result and we see a different behavior. Near resonance, it's still fixed, but significantly less than the classical result. This is a direct result of the fact that the bandwidth of squeezed light is much, much bigger than the broadening gamma EG. So near resonance, there's a lot of wasted energy along the tails of the squeezed light spectrum, which can't contribute to the absorption process. So the potential upshot or downshot of this is that in the far detuned limit, due to the large bandwidth, the cross-section remains constant. And in this region, it's about 2.5 orders of magnitude larger than the coherent light result. But in the far detuned limit, the very far detuned limit, the largest parameter becomes the detuning and everything crashes back down to the coherent light result. So for a lack of time, I won't discuss each absorption term. I'll just discuss A4 and A5, starting with the A4, which was the 2 photon contribution and was generated from the sum of the rephasing and non-rephasing pathways. And here's the classical result, coherent light result. Similar behavior near resonance, it's fixed. It has a 1 over delta squared dependence. And in the far detuned limit, we see a 1 over delta to the 4th power dependence. So we see the pathway involves intermediate populations. So it's more sensitive to the detuning. Now we overlay the squeezed light result and we plot both the cross correlation and autocorrelation. Now our, sorry, I should have mentioned this on the previous slide, but we plot the higher order cross sections as a function of detuning on the x-axis, area per intensity on the y-axis, and in more familiar units of Goppard-Mayer on the right-hand axis. So we'll begin the discussion with the autocorrelation contribution, which is similar to the 1 photon absorption term, below the coherent light result, but fixed. It remains fixed for larger values of the detuning, at which point it's an order, 2 orders of magnitude larger than the coherent light result. And then in the far detuned limit, it approaches a value given by the coherent light result. Whereas the cross correlation term is fixed near resonance, but as the detuning approaches omega E over 2, half the squeeze light bandwidth, the cross section quickly increases to its maximum value. This is a non-trivial scaling of the cross sections with detuning, and turns out to be sensitive to the edges of the squeeze light spectrum. But as we increase the detuning even further, both of them approach the coherent light result. So we find that the autocorrelation contribution is larger than the cross correlation here. And that's because the frequency correlations for the autocorrelation involve, for the rephasing and non-rephasing pathway, frequencies which can be doubly resonant, and it gets a enhancement compared to the cross correlation, in which anti-correlated photons aren't beneficial for this absorption pathway. Next, we'll consider the last contribution to the two-photon absorption, which was A5 and corresponded to the direct quantum pathway. Here's the coherent light result. It's fixed near resonance. It has a 1/delta squared dependence here, a non-trivial scaling with detuning from resonance here, and then in the far detune limit, it depends on 1/delta squared, which is the usual scaling for the two-photon absorption cross-section, which involves a virtual two-photon transition. Again, overlaying the squeeze light results, we begin with the cross-correlation contribution. Fixed near resonance, remains constant. We see this similar behavior where it quickly approaches its maximum value, which is again above the coherent light result, and then approaches a value in the very far detune limit given by the, again, coherent light result. Whereas the autocorrelation contribution is still fixed, still approaches its maximum value at the edges of the squeeze light spectrum, but then it approaches a value below the coherent light result. So here we find that the cross correlation is larger, and this is a direct result of the fact that the cross correlation involves photons which are anti-correlated and always resonant with the two-photon transition, whereas the autocorrelation contribution involves random combinations of photon frequencies. And since the bandwidth of squeeze light is larger than the line width, we see that even in this far detuned region, we see wasted energy along the tails of the spectrum, which can't contribute to the absorption. So we get a smaller cross-section compared to the cross-correlation and coherent light contribution. So we'll take this one step further and consider the broadband far detuned limit, where we define the far detune limit to be when the detuning is larger than half the squeeze light spectrum. And we'll consider just the two-photon absorption term corresponding to the direct quantum pathway. So that was the previous plot where in the bottom right-hand side, we saw this behavior. We saw that the cross-correlation contribution approached the coherent light result to good approximation, and the autocorrelation contribution approached the result below the coherent light result. So we chose our bandwidths to be an order of magnitude larger than gamma FG. So the difference between these two cross sections is not too large, but had we chosen the bandwidth to be even larger, we would see this effect being even more dramatic. So to good approximation, A5 is just going to be given by the cross correlation contribution. And if we neglect this contribution, we see just two scalings with intensity, each of them multiplied by the coherent light classical cross section. And in this limit, we can more directly compare the results to phase earlier result, where we see both the linear and quadratic scaling. And in this notation, at least, the vacuum intensity plays this role of an enhancement factor of the classical cross section. And this is this result was also given by Michael Raymer's group, who considered the very broadband far detune limit in which this high intensity scaling with intensity was found. So we're all here because we're interested in when squeeze light can provide an advantage to coherent light for two-photon absorption. But we have all of these cross sections as functions of detuning, so we can just directly calculate that ratio. So here we plot the ratio of squeeze to coherent two-photon absorption as a function of detuning and intensity, and the color represents the magnitude of this ratio. I just want to point out that we're going to neglect this white region of parameter space because this is the region of parameter space where we determine that the perturbation theory is no longer valid. So a couple of things to point out. First is that in this vertical strip, we see about a factor of 100 enhancement of the squeezed light two-photon absorption. So in this vertical strip, this is a direct result of the fact that squeezed light has a large bandwidth, which can overlap with resonant intermediate states, increasing the value of the cross-section and the overall two-photon absorption. As we decrease the intensity, we see this new regime start, And this corresponds to when the ratio of the vacuum to squeezed intensity is approximately given by 1. So here's the beginning of the usual low intensity or low flux photon pair correlations given by G2, where I think everyone's familiar with the large enhancements that people are discussing. And as we decrease the intensity further, we see that in this regime, the ratio of the vacuum to squeezed intensity is 10 to the 4, which corresponds exactly to the order of magnitude on the. You notice that in this region, we see both effects of the resonant enhancement as well as the low flux photon pair correlations, because again, the ratio of the vacuum to squeeze intensity is 10 to the 4, but the color bar in this region is above 10 to the 5, closer to 10 to the 6. So in this region, we can get both an enhancement from a resonant overlap as well as the usual photon pair correlations. Now, an important question which we wanted to consider is clearly based off this plot, we see that there's a large enhancement of squeeze to coherent two-photon absorption. And at its maximum, it's 7 orders of magnitude. But we wanted to ask, what is the one photon absorption doing or saying in these regions of parameter space? So again, we can just directly calculate the ratio of 2-photon absorption to 1-photon absorption for just squeezed light and compare it in the same regions of parameter space. Again, the x-axis is detuning, the y-axis is intensity, and the color bar is this ratio. And we'll neglect this region of parameter space, which is forbidden as well. So we'll consider the first area where for the ratio of 2-photon absorption, we saw about a factor of 100 increase. And here, however, the 1-photon absorption is in this region of the parameter space 100 times about larger than the 2-photon absorption. In other words, because the 1-photon absorption is also significantly enhanced due to a resonant overlap, it dominates the 2-photon absorption of this region of the parameter space. And even as we decrease the intensity to where we saw the largest enhancement of the ratio of squeeze to coherent 2-photon absorption, in this region for the 2 to the 1-photon absorption, again, the 1-photon absorption is orders of magnitude higher. At its worst, it's in the resonant regime, it's 8 orders of magnitude, and on the right-hand side, it's about 4 orders of magnitude. So in both regions, or in all the regions here, the 1-photon absorption dominates, and the only place where 2-photon absorption dominates is the far detuned high-intensity regime, which is this upper right-hand area of the plot. So now I'll just mention some concluding remarks. We set out to develop a model of 2-photon absorption, which was valid in a wide parameter space. We neglected focusing effects as well as dispersion and considered the response of a single atom or molecule to incident CW coherent and CW squeezed light. We considered the effects where an intermediate state could be near a 1-photon resonance, as well as both the high and low intensity regimes. So in the narrow band of limit, we confirmed previous results and showed that the ratio of 2-photon absorption is given by G2 evaluated at T equals 0. And in the broad band limit, for the parameters we chose, we found 2 regions of enhancement due to a resonant overlap, as well as the usual low intensity photon pair correlation, as well as the combination of these 2 effects. But in both cases, when we looked at the 1-photon absorption, we found that it was that the 1-photon absorption overpowers the 2-photon absorption in most regions of parameter space. So finally, looking forward, there are a few other things which we're interested in. One being the pulse regime, which we haven't considered here, but we can within our model. We'd also like to have a more complete model of the interaction, one where we fully include radiation reaction, and in doing so have scattering as well as fluorescence. An interesting thing also to consider is quantum dots, which have similar properties to typical fluorescent dyes, but are known to have a few orders of magnitude higher 2-photon cross sections. So because of this fact, this could be an interesting region of parameter space to explore. And lastly, we're interested in states of the electromagnetic field after the interaction. So what we mean by that specifically is, how does the photon statistics of squeezed light change due to the presence of a 1 or 2 photon transition? So thank you all for your attention, and I look forward to your questions.
Well, thank you very much, Christian. And I don't think you should ever apologize for giving, a theory talk, even if it is to a bunch of experimentalists. We need both sides of physics if we want to take sides.
Thank you.
Okay, with that, I think we'll open up the floor, and then Mike has already raised his hand, so I'll let you go first.
Hey, do you hear me okay?
Yes.
Okay, that's really impressive work. Congratulations. It's very
Thank
nice,
you. Thank you very much.
very nice to see an extended model that covers so many regimes that are perhaps giving unexpected results. That's very cool. But I have a couple of questions, as you can imagine. One is a minor criticism, which I don't think is super important, but it's a fact that I think you assume that the spectrum of the squeeze light does not change when you increase the gain parameter. And as you know, it really does. The papers, that we wrote and everybody else wrote shows that it does change. But in your defense, it only changes very slightly. The bandwidth only changes like 1/4 power of the pump power, something like that. So it's a very small change, but this whole subject of the JSA of bright squeeze vacuum has been studied in great detail by people like Konrad Banaszak and others. I think I cite those papers in our preprint. So that's us.
Yes, that's a very good point. Sorry. You're right.
Yeah.
You're right. You're absolutely right, though.
Yeah. In fact, Frank Schlavin, I see, is also on the call, and he's also done some nice work using a proper Schmidt decomposition in the bright squeeze regime. So you should also check out Frank's papers. But I think the nice thing about your work is that it gives you a tractable, nearly closed form expression for so many different phenomena that I think it's really, really valuable. Just a couple of quick comments. Well, of course, the obvious one is, we've always been talking about what the absolute signal levels are. And as you know, they're very small signal levels. And the Geneva group has recently convinced us that they can see something, but it takes heroic efforts. And I don't think the question is, does using the resonant enhancement and perhaps going to narrow line systems like quantum dots or atomic systems like the old Kimball Georgiades paper, does that give you a much larger observable signal that would allow one to actually do experiments and observe some of these non-intuitive predictions that you're making?
Yes. So that's a good question. And as I pointed out, for the parameters here, for the specific value of the 1-photon line width, we're not finding that to be the case. Now, I have spent a little bit of time exploring some other regions of parameter space, which, as you mentioned, making me, for one thing, you could make gamma EG, the 1-photon line width, smaller, which would increase the 2-photon absorption. You could also make gamma FG smaller. And in some of the plots that I've generated, I'm not finding that to be the case. That I'm finding a similar situation to here where, again, the 1-photon absorption is larger. So now that's maybe slightly different than what you asked, which is experimentally, does it boost these cross sections into a usable or let's say visible regime? That I don't know the answer to. What I can say is that you do get a factor of 100 times in this region. So I guess my answer would be yes. But again, with the parameters here, the 1-photon absorption is always larger from what I found. It's also enhanced in the same way.
Just to clarify, when you talk about the 1-photon absorption process, that does not lead to excitation of the F state, does it?
No. As we defined it, it's just the lowest order contribution plus the saturation.
Right. So it only reaches to the intermediate state. Right.
Yes.
So if we really care about the F state population, which I think we do, then that's not really a competing process.
So I guess what I mean is, if you based off of at least these calculations, you would see that most of the absorption or the energy removed from the incident field would have a 1-photon signature. It would be to a 1-photon process.
That's right, because you calculated absorption, which I would call a transmission experiment, whereas you're not calculating fluorescence, which is the F-state population.
Yes, exactly. We're calculating the total absorption.
Mhm. But you can identify the different terms. So I guess you know which, the 2-photon process, I guess, would always lead to the F-state.
Yes, so if I just go back a sec, sorry, lots of slides. Yeah, so A3, A4, and A5 do contain a dipole element Fe, whereas A2 and A1 just contain Eg.
Yeah, that's consistent. Okay, thank you.
No problem.
Marty.
Well, thanks for the nice talk, Christian. And thanks for letting us record it. I feel like I'm gonna have to watch it more than once to absorb some of this stuff. But I wanted to ask we've all been, the experimentalists, we've all been arguing that attenuating the pump beam versus attenuating the down conversion is the appropriate way to identify, one of the appropriate ways to identify whether you're actually seeing, entangled 2-photon absorption as opposed to just 1-photon absorption. Have you looked at that to verify that do you agree with that argument that kind of scaling is what we should expect?
Yeah, so I spent some time thinking about it, and if I understand the argument correctly, it's that if you have pairs of photons and you attenuate it linearly, so you remove, for example, a 1-photon transition, then, well, you can't get 2-photon absorption anymore because you only have 1-photon present.
Right.
I think that's basically the general gist of the argument. So yeah, I do. Yeah, like I understand where that's coming from. It would be interesting for us to, yeah, like this would be related to the one of the last points I made, which is it's interesting to look at the output state of light and see how the state of light changes due to these transitions. That would be an interesting calculation to make.
I think it's really interesting too, this point about you're arguing that there can be a significant 1-photon contribution to basically the change in transmission. And
yes.
So it's curious that you might see something under all the conditions the same, you might see a different result sort of when looking at fluorescence versus looking at transmission. That I'm just thinking about
yes, yeah, I see, yes, because that would, yeah, I see what you mean, yeah, because it could also be attenuated from 1-photon absorption.
Yeah.
Yeah, maybe I could just jump in with something. This is something that we're still struggling with, but in this limit where one considers, the 1-photon absorption process may be close to resonance too, as well as the 2-photon process. The actual, what you call 1-photon absorption and what you call 2-photon absorption, that the terms don't break up in such a simple way. It's a bit of a more complicated problem. So there's really I think an interesting, sort of region where 1 and 2-photon absorption sort of are sort of going on together. They're sort of affecting each other, and trying to distinguish between the two of them is maybe not the right way to think about things. But this is something I confess, at least I am still struggling with.
Yeah, a simple decomposition in this way near resonance doesn't really work.
Right. Yeah, I guess if you think about it from the point of view of microscopy, if you want to do 2-photon microscopy, you want the kinds of terms where you're thinking about, you only get strong excitation when you're at the focus.
Yeah.
Right. So I guess you could potentially group things that way if they behave that way. If they're useful for microscopy, 2-photon microscopy that we're thinking about, then those are the ones we really want.
Yeah, and the higher order terms. Yeah, exactly.
Okay, thanks.
Okay, Mike.
Mike's hand is up again too.
Okay. Right. So your theory of line broadening for the molecular system, is it restricted to only Lorentzian shaped lines, or does your R function, can it be like a non-Lorentzian? Because
No,
there's a recent paper by the Mukamel group that calculates the situation when the lines are non-Lorentzian, and typically, you know, the lines will fall off much faster than 1 over frequency in the spectral wings of a line.
So no, both the contribution to the dephasing is a Lorentzian as well as the quantum reservoir. So yeah, everything's essentially Lorentzian here.
Then in the far off resonant regime, that can actually be a very, very bad approximation. And we
Yes.
mentioned that in our much too long tutorial article at the very end. And that's why we kind of even discounted some of the results that we got when we considered the intermediate state resonances, because in the Lorentzian model, the spectral tails are artificially long. And in reality, that does not happen typically.
Yeah. So that's a good point. So then, yeah, if you wanted to compare, if you wanted to use this model, you'd probably have to decrease the broadening, which would, I mean, it wouldn't be perfect, but it would be closer.
Yeah, when you say decrease, it's not just decreasing the line width, right? It's the Lorentzian tail. It doesn't go Lorentzian for large frequencies. And
yeah.
In chemistry, I forget the name of that. It's like a boson model or a Gaussian boson broadening harmonic oscillator model, which is well known to a lot of chemists. And that's what the Mukamel group published last year. So it's a very nice paper.
Yeah, I'll check that. I'm going to check that out. I'm not familiar with that paper.
Yeah, it's even seen in atomic systems. A collisional line broadening doesn't persist Lorentzian form for large detunings. Essentially, you get into a quasi-static regime where it looks like you're averaging over a static distribution of perturbers.
Okay, thank you. Andre.
I think we could extend that. I mean, the kind of dephasing model we introduced, I think could be extended to include some of that.
Mhm. Yeah,
But we haven't done that yet. Yeah.
It's just how you build the reservoir model.
Well, it's 2 parts. Yeah, exactly. I mean, we build it with 2 parts, a kind of dephasing part and a dynamical part. And I think these quasi-static things could be included in a dephasing part, although we haven't done that. It's not.
Yeah.
Thanks, Tom. Andre?
Yes. So when you compare the coherent light with squeezed light, if I understood well, the enhancement is done for coherent light, which is narrowband, while the squeezed light is broadband.
Yes, yeah. We're taking the coherent light to be CW, so very narrow. Yeah.
So is this a fair comparison? So I mean, if you take a coherent light which has the same bandwidth as the squeezed light, what would you get?
So I would say that it is a fair comparison because we're assuming the intensities are equal. So we're assuming that the energy delivered is the same. And yeah, so we haven't considered the case where you have a pulsed coherent light though, compared to a broadband CW state. That we haven't considered.
Because I would expect to compare light, which sources of light which have the same bandwidth, so to say. Yeah.
Yes, yeah, that's absolutely something that we should also do, and I guess within this case we could do it because the coherent light case is simpler.
Yeah.
So I don't necessarily agree with Andre. I think it is fair to compare a pulse of light that has the same temporal duration and the same amount of energy delivered. I think that's what Christian is doing. And if it's a coherent state pulse, the bandwidth is just determined by the pulse duration. And so it's true that Christian has treated only the limit of long pulses, which is perfectly fair. I don't think you,
But still, those pulses do not have the same bandwidth as the squeeze light. So that was my point.
I don't care about that. I just care about how much energy is delivered in a certain amount of time. And that's the efficiency of the process. From a practical point of view, I think that is a good comparison. Maybe from a more intellectual point of view, what you're saying, Andre, is correct because you want to understand the physics. But I think in a practical sense, it's how much energy is delivered in a certain amount of time. But that's debatable. I follow that.
Yeah, still, it would be interesting to do that comparison. We should do that, yeah.
Oh, yeah.
Jadon,
We do that.
Oh, yeah.
sorry.
Oh, sorry.
We do some of that in some of our papers. Oh, go ahead.
Yeah. It's a very nice talk. So I think I'm wondering if you are using the single mode squeezing or two mode squeezing light.
So it would be single mode because, sorry, one second. There's no polarization dependence here.
Oh,
Yeah, I would
okay.
call this single mode.
Okay. So how do you think about if using the two mode squeezing, for example? Yeah. So because
Yes.
For comparison, if you compare your results by using the squeeze light with the entangled photon pairs, which people did a lot before, and for those cases you have to entangle the two mode, you have to entangle the two modes of the photons. So in this sense, I think maybe it might be important to consider the two photon absorption using the two mode squeezing light. So what do you think?
Yeah. So that's a good question. I will maybe revert you to one of Michael Raymer's recent papers where they actually considered that. But effectively, the difference is that in the correlation function, you don't get this third contribution because the photons are distinguishable.
Yeah, exactly.
So that's the main effect of taking that situation.
Okay, yeah.
But for a more detailed answer, you can check out his paper.
Okay, but another related question is what will be the major difference between the squeezed light result and with the the result from the entangled two photons? I mean the entangled photon pairs.
Yeah, so I don't think that there is a significant difference in the scalings with intensity.
Yeah, but I think the efficiency of the two photon absorption by using the squeezed light is is lower than the efficiency to using the entangled photon pairs for the low photon flux.
Yeah.
So which you can find from this result. You can find this result from the Girish-Agrawal's paper. Published a few years ago.
Sorry. So you're saying that using a two mode squeeze state compared to a single mode squeeze state, the two mode squeeze state.
No. Using the squeezed light, the cross section of the two photon absorption compared to the entangled photon pairs, the entangled twin photons, and I think the efficiency at very low flux is still lower than the one using the entangled photon pairs, right?
Yes. So you're talking about, I think this here, where the contribution in which the photons are correlated does better than the ones which they're not. Is this, I think, what you meant for the cross section?
No, not really, because if you are using the entangled photon pairs, and which has the very highest entanglement between the photons, and the squeeze light, and then that's why I think Girish-Agrawal's paper showed. If I remember correctly, they showed the cross section and the efficiency. It's by using the squeezed light is lower than the one using the entangled photon pairs. But here we assume the very low photon flux.
I see. Okay, so sorry, I'm still a little confused. I guess if you had a low flux, photon pairs would, well, I mean, if you have a squeeze state, you'd also have pairs. So I guess I'm not, anyways, maybe I just need to take a look at the paper. I'm sorry, I'm still a little bit confused.
Okay, yeah. So that's also the question which I like to understand. So yeah, if the how I mean what is the comparison between the two-photon absorption using the squeezed light and the entangled twin photons?
What's the paper you referred to?
I think it's APL on the applied physics letter by Girish Agawa.
Oh, by Girish Agro.
Yeah.
Could you put that paper in the chat box? I'll take a look.
Yeah.
Yeah. Let me find its citation. Yeah.
Because we all think that in the limit of low flux, squeeze light is identical to entangled photon pairs.
Yeah. I mean, there's your point, Mike, about the fact that the joint spectral length changes with the pump and so on, but.
Okay. Yeah. One, but in the limit, I think I agree. It's a very, very extremely low photon flux. These two lines will merge together. But what happens if we increase a little bit, for example, the photon flux, and I think the photon entanglement will play a significant role. But the photon entanglement and for the squeezed light is still lower than the entangled twin photons. Although the photons, the intensity of the light of the squeezed light, of course, is larger than the entangled photon pairs.
So I guess I'll say that here for this work, we do find that the autocorrelation contribution approaches a value below the coherent light result, and the cross correlation where photons would be correlated, the cross section at least does approach the classical result, which is the point that Michael Raymer was making. And in terms of your other comment, the intensities that we're using, it's just one intensity here, the intensity of squeeze light. That's all we're considering. That being in the low limit and the high limit. And yeah, so I think I'm not sure I'm following. But yes, in the low intensity limit, we do see a strong enhancement, which is the usual enhancement people talk about. It's not a new point though.
Yeah, that's fine. Yeah. I also have to double check. Yeah. Yeah.
Okay, thanks. Frank, I see you've raised your hand as well.
Yeah. Thank you. Yeah, thank you.
So also from my side, thanks a lot for this talk. That was very interesting. I would like to come back a little bit to the discussion that Andre had raised about, whether we are comparing like for like when you compare a CW coherent state with your CW squeeze state. And I mean, you said earlier that you're considering a single mode squeeze state, but I don't think this is true, right? I mean, you have these broadband fields. And so you will require, if you do a Schmidt decomposition of your joint spectral intensity, you will see that you will need many modes to describe your squeeze state, I suppose.
Yeah, you're absolutely right. I think it's just bad language of one mode and two mode and multi-mode. But you're absolutely right. Yeah.
And so I guess my question would be, when I look at your plots of these absorption cross sections and so on, how much could I shift them by changing parameters of my squeezed light in your simulations? That's why, for instance, from my side, my solution was to always look at optimized states of light for a given sample system, and to look at how much absorption cross section can I possibly get out if I look at an optimized state of light. And so yes, for instance, in this picture, I mean, you told us that, for instance, on the left-hand side, if you're weakly detuned, you have all this spectral amplitude of your broadbands, that cannot contribute to the absorption cross-section. What if I instead choose a more appropriate squeeze state, which is also narrow in resonance in frequency? Then you would still have some enhancement due to, I suppose, the photon statistics, but you would probably have fewer losses due to the broad bandwidth, right? So I guess so my question is, how much can I shift these plots up and down by changing the parameters? that are somehow
Yes.
hidden?
Yes. So one thing you could do is, as you mentioned, decrease the bandwidth. And what's going to happen as you do that is essentially both of these plots, the blue and the green, are going to lift up and actually match the coherent result. Because that's one thing we can show mathematically that that's the case. Now, you know, it depends on if you're interested in decreasing the bandwidth and also seeing a resonant overlap, that's going to contain, or that's going to involve specifying more parameters. You just want that the bandwidth is wherever you want the resonant enhancement for the in the detuning, you want the bandwidth to overlap that. So in changing that, you'd also change these peaks. You could move them left to right by changing your bandwidth. So if you chose a smaller bandwidth, you could move these peaks to the left as well, because then you'd need a smaller detuning to get that resonant enhancement. I guess what else could you do? Well, you could change the line widths, which would also change the magnitude of these contributions. Sorry, am I like fully answering your question, or is there more?
Yeah, no, in some sense, yes, that's what I would expect. Can you, I mean, would it be possible to produce a plot where you kind of show, you know, how far you can get? So, you know, in a sense, you're always comparing two different states. What if you make a plot of the maximal enhancement that you can get if I choose the optimal state for each delta? Would I ever fall below the black line, or would you get something that is always better than the coherent state?
Yes. I don't know the answer to that because I haven't considered it. But naively, I would guess that there will be a point in the far detune limit where squeeze light does better. But I you know, as I said, I haven't done that, so I don't want to be, you know, don't quote me on that, but it seems like that would be possible to me.
That's a good suggestion. That's not so hard to do. And
I'm sorry, I don't have a better answer. I haven't considered that. But it seems like if you're far detuned for coherent light and you always have a squeeze state that has a large bandwidth that can overlap with that transition, yeah, I'd expect a squeeze light enhancement there.
Yeah, thank you.
Okay, I don't see any other hands raised or any questions in the chat. If that's the case, I think we've sort of had quite a nice discussion, and like